We've looked at a bunch of different forces now. Normal force, which is the force of the floor pushing up at 90 degrees, the force of gravity, the force of the center of the earth pulling down on something, right? We talked about a little bit about the force of friction in terms of here's the value of friction. We haven't really learned how to find what that value of friction is, though. Let's spend a little bit of time today talking about how to determine that force of friction. Not just here's the force of friction, how do we account for that? How do we use that? But what is the force of friction? How do we find that force of friction? Before we do that, we should probably define friction. Friction is a resistive force. You know what that means? Resistive force? What do we mean by that term? Resistive. Yep. Almost. It always opposes, starts with an M. I'm looking for M. It always opposes, no, it always opposes motion. It always opposes motion. So it's a force that always opposes motion. Now, normally, Ben, you're right, that does oppose the bigger force, but there are exceptions to that, and we'll point that out in due time. But right now, just know that it always opposes motion. If something's moving to the right, then friction is going to act to the left. If something's moving forward, then friction is going to act backward. It's a resistive force between two surfaces that oppose motion. There's a force of friction between your tires and the road. When you drove in this morning, that force of friction was probably fairly large. They're calling for snow this afternoon. When you go home this afternoon, the force of friction between the tires and the road will likely be less. The resistive force, which in this case is a good thing, the resistive force between those two surfaces, your tire and the road, is going to change as the composition of the road changes from pavement to slush or ice. So friction is a resistive force that opposes motion. There are two types of friction that we started talking about the other day. The first type is kinetic friction. The other kind, by the way, was called static friction. Kinetic friction is a resistive force that acts between two surfaces when an object is moving. When an object is sliding or skidding, it experiences kinetic friction to oppose its motion. So if I have a desk that's sliding along the room, somebody gave the desk a push, sliding along the room, there would be kinetic friction that will oppose the motion of the desk. Anybody a curler here? Anybody go curl at all? There's a resistive force of friction that acts on the curling rock as it slides down the ice. Now, which is a higher resistive force of friction? The force of friction between the desk floor or between the curling rock and the ice? Which one is a higher friction? Clearly, the desk and the floor has a higher resistive force, right? I push this desk and it slides maybe a meter, probably not that far. When I push a curling rock, it slides usually all the way down to the other end of the ring. There is a resistive force of friction, kinetic friction, because it's sliding, but it's not as great. Now, I'm going to give you a couple of other names for this kinetic friction force as well. We have kinetic friction. We can also call it dynamic friction. Those are both real names for this. So sometimes you might see the term kinetic friction, sometimes you might see the term dynamic friction. They both mean exactly the same thing. Another name that I sometimes give to it is sliding friction. I put that in quotation marks because that's not a real name for it. But I use that term sometimes because I think it helps us to understand what's really happening. Sometimes we can have movement with static friction, and that's confusing. But if we always think about something as either sliding or not sliding, then it's easy to differentiate between the two. The curling rock is sliding on the ice. That would be kinetic friction. The desk is sliding along the floor. That would be kinetic friction. Hopefully, at least, when you're driving your car, the tire is not sliding along the road. So that would actually be static friction because it's not sliding. There's movement, right? But it's still static friction because it's not sliding. So the type of friction that acts on an object when an object is already moving or when an object is sliding or skidding, aka also known as dynamic friction or sliding friction. Now, there is an equation that helps us to find fairly easily the magnitude of this force of sliding, dynamic, kinetic friction. We will say the force of kinetic friction, the magnitude of the force of kinetic friction, these absolute value signs around it, indicating that although kinetic friction is a vector, we're not going to get the direction out of this equation. It will only give us the magnitude, how big the force of friction is, not which direction it's acting. That's okay. We always know friction opposes the motion. If an object is moving to the right, friction acts to the left. We don't need an equation to tell me that. If the curling rock is moving forward, friction acts backwards. I don't need an equation to tell me the direction of that force of friction. That's good, because this equation won't give me the direction. It'll only give me the magnitude, the size of the force of friction. It is equal to mu. That's a Greek letter. Alpha is a Greek letter. Beta is a Greek letter. Gamma is a Greek letter. Delta is a Greek letter. Remember way back in 2020, the Delta variant of COVID? Then we were on the Omicron variant. Remember that? And now it's all just a bunch of subvariants. They were all named from Greek letters. Okay, the Delta variant, the Omicron variant, the mu. They could have gotten to the mu variant. It just never has gotten to the mu variant. Mu is a Greek letter, just like alpha, beta, gamma, delta, Omicron. The Greek letter. So mu, whatever that means, with a subscript k, times Fn. What does Fn stand for? Yep, the normal force. Normally, the normal force is the same as gravity. If we're talking about the curling rock on the ice, gravity pulls down on the curling rock, the normal force pushes up with the same value as gravity pulling down. So we just say, well, calculate m times g, that's the normal force. The desk, as it's sliding along the floor here, there's a force of gravity acting down, there's a normal force pushes up that balances gravity, so normal force would just be the same as the force of gravity. There are exceptions to that. If I'm on a surface like this, gravity pulls down, the normal force pushes up like this, and then remember F parallel goes like this. We would have to find the normal force. It's not that hard. F parallel, we use the sine function to find F parallel. We could use the cosine function to find Fn. We need Fn. Most times it's just m times g, but occasionally it is something different than m times g. We'll deal with that in due time. What's mu stand for? I told you it's the force of friction is mu times the normal force, measured in newtons, and usually that's going to be just m times g. What does mu stand for? Yeah, it's what we call the coefficient of kinetic friction. And that coefficient of friction is just a measure of how much two things stick together. There is a higher coefficient of friction between the desk and the floor than there is between the curling rock and the ice. The desk and the floor stick together way more than the curling rock and the ice. There is a higher coefficient of friction between your tires in the road this morning on dry pavement than there is this afternoon on, presumably, at least the weather forecasters are calling for, snow and rain this afternoon. There will be a lower coefficient of friction this afternoon, which means the tire and the road don't stick together as well as they did this morning. That's why we have to be super careful when we're driving on snow and on ice and on rain. Make sense? There are no units associated with that. It's just a number. And typically that number is less than 1, although it doesn't have to be less than 1. Dry pavement and rubber tends to be about 0.8, 0.9. Wet pavement or icy pavement in rubber tends to be like 0.2-ish. So quite a bit less. It's possible to get a number that's bigger than 1, 1.1, 1.2. That's not overly common, but it is possible to get that. So far, so good? So we've been talking about there's two types of friction, right? Forces that resist motion. We've been talking about the one type, kinetic friction, dynamic friction, or what's the word I use for it? Kinetic, dynamic, or sliding. When something is sliding, it has kinetic friction. Got it? When something is sliding, it has kinetic friction, or dynamic friction, as we call it. Let's take a quick peek at this example here. 1,700 kilogram car sliding on pavement. The coefficient of kinetic friction between the rubber tires and the car pavement is 0.80. What's the force of friction acting on the car and the acceleration of the car? We've got a mass here of 1,700 kilograms. We've got a coefficient of kinetic friction of 0.80. We're looking for the force of, it would be kinetic friction or dynamic friction or sliding friction, and we're looking for the acceleration as well. So we're going to say FKF, the force of kinetic friction, or at least the magnitude of it, is mu times the normal force. Mu is 0.80. And the normal force, assuming this car is not going up or down, which I think that's a pretty safe assumption, and assuming the road is flat, then the normal force will just be the same as gravity, right? So it will be 1,700 times 9.81. There are, again, exceptions to that, right? When you drive on the highway, you might notice that the road, this is an exaggeration, but the road kind of peaks in the middle usually. And it slopes down to the side. You know why they do that, by the way? Yeah. Okay. I don't think that's the main, that definitely wouldn't be the main reason, but that could be an effect of that, yeah. If you were to fall asleep or something, you'd be more likely to go into the ditch as opposed to opposing traffic. Yeah, it's meant more for drainage, right? We don't want water to be pooling on the road because that creates a whole other issue, right? You ever driven a car in the hydroplane where you kind of skip along the water, right? Like skipping a rock along the water, and you lose complete control of your vehicle if you're hydroplaning. We want to avoid that. So they have the water drain off the highway like this. But the effect of that is, if you're looking at this from behind, these are the wheel of your car. The effect of that is that the normal force is not 9.81 now. This would be gravity. So the normal force isn't the same as gravity. The normal force would be the adjacent side of that triangle. But we're going to assume the road is flat, and therefore the normal force is just the same as force of gravity. It balances the force of gravity. Okay, let's calculate this here. Let's say 0.8 times 1,700 times 9.81 gives me a value of 13,341.6, which we're going to round to 2 digits. The first zero does not count. The second zero does count. So this would be a 2-digit piece of data there, the coefficient of friction. We're going to say 1.3 times 10 to the 4 newtons. So it says, what's the force of friction? Well, the magnitude of the force of friction is 1.3 times 10 to the 4. The actual force of friction would be 1.3 times 10 to the 4 backwards, right? Car's going forward, friction is going to act backwards. So technically, negative 1.3 times 10 to the 4. Make sense? Now, how do you find the acceleration? This isn't very hard, actually. The acceleration, this is the hard part. The acceleration is just F over m. Now, I'm going to make the force negative 13,341.6. How come I made it negative? This equation gave me the magnitude. If I'm going to put absolute value signs around here, then all I got to do is sub in the magnitude of it, right? But if I'm going to actually find the direction of the acceleration, which I can do, then I have to include the direction of the force, which is opposite to the motion. I'm moving forward, the force is backward. So we're going to make it negative here. Divide that by 1,700 kilograms, and that gives me a value of negative 7.8. I'm going to say meters per second squared. I could have also said meters per kilogram. I get a negative value of acceleration. What does it tell me? It's completely consistent. What does it tell me? That I get a negative acceleration. Slowing down, of course I'm slowing down. That's what friction is going to do to me, right? When you're skidding on pavement, I hope I'm going to slow down when I'm skidding on pavement. I don't want to speed up or keep going at a constant speed when I'm skidding. I want to slow down. Now, I'm going to slow down pretty quickly here because the coefficient of friction is pretty high here, right? My acceleration will be less if I was skidding on ice because the coefficient of friction would be less. That makes some sense, you guys? Okay, now one more little thing that I want to mention about kinetic friction here, right? Sometimes we see a problem that's as straightforward as what we see up here. And that's great when we do. We could absolutely expect to see something that's on a quiz or a test. But sometimes we see a question that's worded a little bit differently, kind of a little tricky. Question might say, a force of 15,000 newtons is required to keep an object moving at a constant speed. A force of 15,000 newtons is required to keep an object moving at a constant speed. If I'm moving at a constant speed, that means I'm in a state of, we talked about this earlier today when we were doing something else. If I'm moving at a constant speed, I'm in a state of, starts with an E, equilibrium, specifically translational equilibrium, right? Versus that sign problem that we did that was static equilibrium. I'm in a state of equilibrium. That means force is balanced. So the forward force must equal the backward force. And the backward force would be friction. So if I said a 15,000 Newton force was required to keep an object moving, the applied force is 15,000 newtons, required to keep it moving at a constant speed, that's telling me that the force of friction must be 15,000 newtons. So I'm telling you what friction is in that case without telling you what friction is in that case. If we're moving at a constant speed, the friction force must be the same as the forward force. So if you're ever given a question, and you will be given a question, that says, here's the force required to keep it moving at a constant speed, what we're really giving you there is the force of kinetic friction. Does that make sense? All right. I want you to skip an example, a couple examples here, and take a look at example number 5. We'll go back and do those other ones in a bit here, but just focus on example number 5 right now. This one says a force of 40 newtons is required to keep a 10 kilogram object moving at a constant velocity. What's the coefficient of friction between the object and the floor? First of all, what type of friction are we looking at? Yeah, it would be kinetic friction because we're moving, right? Presumably we're sliding here. This would be kinetic friction or sliding friction or dynamic friction, whatever you want to call it. I'm okay with any of those terms. Now, we're not given the force of friction here, are we? We're given the force that I'm pulling with. I'm pulling with 40 newtons forward to keep it moving at a constant velocity. But if I'm moving at a constant velocity, then we know I'm in a state of, we just said this, equilibrium, specifically translational equilibrium. And if I'm in equilibrium, then forces must balance. So the force pulling forward at 40 newtons, that must balance the force of friction that's acting backwards. Friction's therefore got to be 40 newtons. So in a little bit of a roundabout way, this question is telling you that the force of kinetic friction is 40 newtons. So let's write that down as a given. FKF, the force of kinetic friction, is 40 newtons. They're telling me without telling me. Right? Here's the force that's required to keep it moving at a constant velocity. All right. Then we're in a state of equilibrium because it's constant velocity. Therefore, the force that I'm pulling with to keep it at constant velocity has to equal the force that pulls it back in the other direction, which is friction. The forces have got to balance. My mass is 10 kilograms here. And I'm looking for the coefficient of kinetic friction. That mu, by the way, it's not an M, it's not a U, it's a U. Kind of looks like an M, kind of looks like a U. It's mu. Sometimes people have a little trouble writing the Greek there. All right, let's say FKF, that is equal to mu times the normal force, mu K times the normal force. And let's rearrange that to solve for mu K. So we divide by Fn. The force of kinetic friction is 40 newtons here. Right? They didn't tell me that, but they kind of did. They told me that the forces that were required to keep it moving at a constant velocity is 40. The force that I pull with to keep it moving is 40. Well, if it's in equilibrium, which it is because it's at a constant speed, then the force that gets pulled back by friction is also 40 newtons. The normal force here, well, assuming it's on a flat horizontal surface, it would be the same as gravity, 10 times 9.81. So let's do this now on our calculators. Let's say 40 divided by bracket 10 times 9.81. Don't forget those brackets on the bottom because then we're doing an operation. Gives me a value of 0.408. There we go. There's the coefficient of kinetic friction. So this question could have said, the force of kinetic friction is 40 newtons, the mass is 10 kilograms, and what's the coefficient? You guys would have nailed that. This is the same question. If we're moving at a constant velocity, this is the same question. Just recognize that applied force has to be the force of kinetic friction, but only if you're moving at a constant velocity. If you're accelerating, that wouldn't be the case, because we're not in a state of equilibrium and the forces don't balance there.